So Peter, I think the floor is yours now, and so we were happy to have Peter Morgan speaking math physics seminar, and it's a Zoom this time because he's from
You have it.
okay. Okay, Peter, it's yours. Yeah.
So, thank you. So, I want to give you some sense of why I find it very helpful to think in terms of signal and data analysis when trying to understand quantum mechanics. So, I'm going to start off with a fairly elementary discussion just of algebraic quantum mechanics and classical mechanics, and then immediately start talking in terms of signal analysis about quantum field theory and applying the same kind of thinking to renormalization. Then I'll have just one slide indicating how I think that can be used towards quantum gravity. And then, as well, applying a signal and data analysis kind of thinking to measurement incompatibility and the measurement problem. And then finally, just a single slide about intervention and causality as a way to think about measurement incompatibility in a kind of classical way, but not quite. So, algebraic quantum mechanics and classical mechanics. There are abstract measurements, M1, M2, M3. We can add them together. We can multiply them. We have linear operators that correspond to random variables, and the spectrum for a linear operator corresponds to the sample space for the random variable. Then the multiplication can be non-commutative, in which case we say it's quantum mechanics, or it could be commutative, in which case we say it's classical mechanics. And then there are a number of other algebraic properties that I'll assume just because I want to make a connection with quantum mechanics. So that gives us just abstract measurements. We want also to make contact with physics, expected measurement results. And there's a standard way in the literature of doing so that makes contact again with quantum mechanics, which is to introduce a state that satisfies these four properties. And in particular, we get the expected value for M1, but also all the moments for the probability distribution associated with that. And so we can construct a measurement generating operator that gives us the characteristic function that generates these, and we can take the inverse Fourier transform of that to give us a probability distribution. So these four conditions just are positivity because probabilities are positive, normalized because probabilities add up to 1, linear because linearity for probabilities, but also even if A and B do not commute so that we make contact with quantum theory. And then we also require, because probabilities are real valued, this commutative diagram. So we can also use the measurement operators to modulate the state. So using signal analysis sort of language here, because we can take an operator A and its adjoint and bracket them around that measurement operator, and this construction also satisfies the rules for it to be a state. And this allows us to use the Gelfand-Naimark-Siegel construction of a Hilbert space. And that puts us into the land of quantum mechanics really quite solidly. And we can also we can use GNS construction to represent the state as a vector and a covector bracketed around the measurement operator, and similarly for the modulated states. So for quantum mechanics, we have measurements 1 through n, for which we also need descriptions of those measurements so that we can know what we're doing when we do an experiment. So I'm going to put those together. And instead of having the index set be 1 through n, I'm going to make the index set be rather more complicated. It's going to be descriptions instead of just 1 through n. And this is very much anticipating quantum field theory, for which measurement operators we construct by smearing an operator value distribution with a test function to give us an F measurement, as I'm going to call it. So the F has taken the place of subscription, a much more formal sort of thing than a description. And indeed, these measurements, these test functions, as mathematics typically calls it, we also can call smearing functions. In signal analysis, these are called window functions because they tell us what we're looking at, so to speak. And I'll also call them modulation functions because we can modulate a state by using them, by applying them to a state. And these are all descriptions of how a measurement is different from point-like. It might be very small, it might be oblate and cubic or whatever. The test functions tell you what the measurement is. So for quantum field theory, we require that F measurements must commute with G measurements if the supports of those test functions are causally or space-like separated. Whereas we can also think of what I'm going to call a quantum non-demolition field theory, where an FQND measurement always commutes with a GQND measurement. And I'm adopting this language of a quantum non-demolition from the quantum computing and quantum measurement theory literatures. But we could also, and have in the past, called this a classical algebraic random field theory because it always commutes with itself. And we can also think of it in terms of signal analysis as a noisy signal analysis in 1+3 dimensions. And later in this, fairly soon, I'm going to talk about how we can construct an isomorphism between quantum optics and QND optics. So for quantum gravity, we can do something similar to this. We can describe how we measure the geometry of space-time instead of modeling what the geometry of space-time is. We can back away from wanting to say everything about how the world is and just talk about the measurements we perform to be able to say something. So this is in some ways an empiricist path, but mathematically it's a dual formalism because we want to work with the test functions, which is a relatively well-defined space, as opposed to with the operator value distributions, which are to which we, for instance, can't do multiplication in any straightforward way. So this is a crude schematic of how I see an experiment. We have whatever it is that's contained by the experiment is surrounded by many devices, and each of those devices has a signal line to a piece of hardware that converts that signal as it receives it here to some kind of compressed digital form, which is then recorded in computer memory, and then subsequently we analyze that data, we write a paper, and so on. Now, typically, we record from here when an event happens. On the other hand, we could, and some experiments do, record every picosecond what the signal level was out of the device that we're using. So I think that quantum field theory and signal analysis are both grounded in those actually recorded experimental data. But it is a lossy compression of the noisy signals. Even if we record every picosecond, still we could have been recording every femtosecond. And from that data, which we want to be enough to make some kind of inference about what we can say about whatever there is out there. So we want to be realist at that level. We want to be able to say something. But even so, it seems to me that it's very worthwhile to hesitate before we say that a particle or system causes the events that we see in those devices. Better to wait until we've really completed the analysis before we make such an assertion. And I find it also helpful not to talk about a field that is measured. The mathematics of a quantum field theory is about measurement operators. It's not about what we measure, it's about the measurements we perform and descriptions of those measurements. This is the mathematical structure we use. So, to really dive into the specifics for a free field, I think it's helpful to think of the vacuum state as a noisy carrier signal, which is broadband because it's not a single frequency, nor do we have any phase information, but we're going to modulate the probability distributions. It's not like a radio signal where we're going to modulate the signal. We're going to modulate the probability distributions. It's a much more sophisticated system in that respect. It's a higher order mathematical system. So if we look at the vacuum state, we can take an F measurement, generating operator to construct a characteristic function, which of course for the vacuum state for a free field is a Gaussian. We can take the inverse Fourier transform of that and obtain a probability distribution for those measurements. And this F comma F is a pre and a product, which is the smeared 2-point vacuum expectation value. And the other mathematical structure we have in here is the complex structure on the test function space. So those two things determine all the geometric structure, and much of this, however, is the algebraic structure. And so we can modulate this normal distribution, which is the free field vacuum, by what I'm going to call a G-coherent modulation, by bracketing the generating operator here with a unitary operator constructed with the G measurement operators. And that gives us a displacement where the displacement will depend on how much overlap there is between the F and the G functions. So it varies across space and time how much displacement there is when we impose a G-coherent modulation. But of course, we can do something more. We can also modulate by just using the G measurement not as a unitary modulation. I'm going to call this a G-rays modulation, where you might call it a single particle state. But it gives us this probability distribution just out of the math. And all this is just pursuing the mathematics of the algebra of observables that we have. And of course, if we use a polynomial here, then we'll get much more sophisticated, much more general probability distributions. So the modulations can be really considerably more complicated. We can also modulate joint measurements. And I'm going to call this a Wigner characteristic function, because if these measurement operators do not commute, then we will not obtain a probability distribution when we take the inverse Fourier transform. But if they do commute, then we obtain a probability distribution, joint probability distribution. Now, all of this is entirely local properties of the field, which could be scalar, it could be anything. The pre-inner product contains what the structure of the field is. If we want to use more global tools, then I will only talk very little about those today. So the reason I wanted to introduce the Wigner characteristic function is because if we fix it, we can fix the algebraic structure of the algebra completely. For the Gaussian state in particular, we can separate it into a Gaussian noise factor and a non-commutativity factor by using the Baker-Campbell-Hausdorff identities, which becomes a noise term and a non-commutativity term. And that fixes the algebraic structure of the commutator. Now, although I've constructed this by thinking in terms of an ordinary Gaussian free field, for this rho v to be a state, FIFJ just has to be a positive semi-definite matrix. That's all that's required algebraically for this to work as a statistical state over the measurement operators, the F measurement operators. So we fix the algebraic structure. We can fix the geometric structure in multiple ways. So we have, for the smeared 2-point vacuum expectation value for the Klein-Gordon field, we project to the forward mass shell, and we multiply the wave number components for the F and G functions. For quantum optics, we have almost the same construction, except for bivectors. So we project to the forward like cone. We construct two space-like 4 vectors, which are both orthogonal to the wave number, and this comes out also as a positive construction, positive semi-definite construction.
Could I just ask the property you mentioned in the middle line that the 2-point function FIFJ is positive semi-definite? I assume that's not automatic, or is it automatic?
For the case of the free field, it's automatic because it's a pre-inner product.
Right.
In general, you will construct it in a similar kind of way, of course, but it needn't necessarily be linear, which will be crucial later in the talk.
Okay, I got it. Thanks.
So these, of course, are manifestly Poincare invariant. What we've got here is only a finite number of measurement operators. So this is perfectly enough to do physics or to do engineering. We might have thousands or millions of such things, but we don't need a continuum. If we want to be doing mathematics, then we may well want to work with the representation space of the Poincare group, for which we can construct that by using a direct or inductive limit over Schwartz space, and that gives us the Gaussian Fock space we're accustomed to. But in this construction, all we have to do to obtain a Gaussian quantum non-dilution field is remove the theta k0 from here so that we have both positive and negative frequencies. This is different from what you'd expect for classical physics because we have h bar instead of kt, and it's Poincare invariant instead of not being Poincare invariant, which would be the case for a thermal state. But nonetheless, this is an everywhere self-commutative field. It's a QND field, as I've been calling it. So to further make very specific what this relationship looks like for quantum optics and QND optics, I'm first going to construct the same Gaussian state in a slightly more familiar way by constructing the F measurements in terms of lowering and raising operators, and for which the commutator is the same pre-inner product as we had on the previous page, and of course the lowering operator annihilates the vacuum. And that gives us the commutator as you'd expect and satisfies microcausality. But for quantum optics, we can find an involution, what I'm going to call the bullet involution, for which this expression is 0. And that means we can construct an FQND measurement for which this construction satisfies the trivial commutator. And of course, this is not the same, well, not of course, it isn't the same as an F-bullet measurement because the star and the bullet are in the opposite order in that case. So these generate a QND optics field, commutative algebra of quantum non-demolition measurements, and the Hilbert space is isomorphic to what we had for quantum optics because we use the same raising and lowering operators and the same vector, the same vacuum vector. But of course, the algebra generated by the FQND measurements is not isomorphic to that generated by the F measurements here. But if we're willing to introduce a Poisson bracket, which is not an unreasonable thing to do, given that this is purely commutative structure, or if we're willing to use raising and lowering operators freely, or if we're willing to use the vacuum projection operator, any of those three constructions will allow us to model anything that can be modeled in quantum optics with QND optics also. So, to be absolutely specific about the bullet involution here, all we have to do is there are multiple possibilities. One possibility is to project to the left and right helicity components and change one of those two components in this way, introduce a different relationship with negative frequencies. And this bullet involution is Lorentz invariant, but it's not translation invariant or local. But that doesn't matter because quantum optics and QND optics are both Poincare invariant. So this is not something that we ruled out because it's not Lorentz invariant. So axiomatically, what does this look like? We have the Whiteman axioms. We've been studying them for decades, and we've not been able to construct any interacting models. Somehow, these axioms are too tight. All it requires is there's a Hilbert space that supports a unitary representation of the Poincare group. There's a lowest energy Poincare invariant vacuum vector. The quantum fields are operator valued distributions. They're linear maps. Quantum fields can be Lorentz scalar, vector, or if it's electromagnetism, bivector. The microcausality is required, and completeness is required so that the F measurement operators acting on the vacuum vector generates all of the Hilbert space. But if we think about this in a signal analysis and quantum non-demolition field theory way, there are three ways in which the Whiteman axioms look much too strong to me. One is that for a quantum non-demolition field theory, we should allow the vacuum to be not a purely lowest frequency state. So now I'm not going to call it lowest energy, I'm going to call it lowest frequency, because in the classical signal analysis, negative frequencies aren't energy. If we're working with signal analysis, we have for the real signal, we have cosine of omega t with the phase. Whereas for the analytic signal, we have we can call this either positive or negative frequency, but still it's only positive or only negative frequency. And we use something like the Hilbert transform to go between these two things, which looks very similar to the bullet operation I introduced on the previous slide. So that's the way in which to think about this in signal analysis terms. And of course, for quantum non-demolition field theory, we also allow commutativity at all separations. But what I want to talk about in the next few slides is I want to argue that we should allow quantum fields to be nonlinear maps into the algebra of measurements. And first, I want to point out there are two linearities implicit in the Whiteman axioms. States are linear, as I saw on the third slide, to ensure that there's a probability interpretation that I don't want to call into question today. On the other hand, F measurements are axiomatically linear in f of x precisely because we say it's an operator value distribution. But if we're doing signal analysis with f of x as a window function and g of x as a modulation function, with the inner product between them as a resonance between those two measurements, then linearity of the field is not so obvious that it should be axiomatically forced upon any mathematics we do. Now, that's not a strong argument, I feel, but nonetheless, if we look at real space renormalization, we find nonlinearity in a rather similar sort of way. So if we suppose that an f of x is a modulation function that's defined, has support only on this region, this square region, and we split that into 9 fragments, Then we measure in each of those 9 fragments what the result of the measurement is, and we project to either plus or minus values. We add those plus or minus ones together, and we get either plus or minus 1 because we project to either plus or minus 1. So this is an obviously nonlinear construction. We iterate it many times when we do real space renormalization, but it's arguably still a quantum field, and it particularly still, by construction, still satisfies the microcausality, because it's entirely local to the support of F that we started with. So this suggests, I think, that we should allow and expect F measurements to be nonlinear in the test functions. So if we look also at the renormalization group, we find, and I'm going to follow Hollowood's book from 2013, in which he suggests that we think of a measurement F as a function of interaction parameters, of a characteristic length scale, and of either mu or mu prime as 2 different choices of cutoffs. But then, no matter what the choice of cutoffs is, the content of renormalization is that these 2 expressions should be the same. They both should give the same measurement results. But L is just, it's hopelessly undetailed. You're putting your finger in the air and saying, well, this is like a nuclear experiment, or this is like a Higgs scale experiment. We should be looking at the details of how we describe the experiment. And so when we talk about the experiment results, it should be a function of all the test functions we would use in a detailed description of the experimental apparatus. And when we look at the cutoff scales, well, surely the same should be true there. Everything should depend on the details of how the experiment is constructed, how we describe the whole experiment. So instead of just taking mu and mu prime to be just finger in the air, bigger than L, we take mu to be some functional of the test functions. So as we change the test functions that describe the experiment, so mu will change as well. That also fixes an effective dynamics. But now we have this emboldened F, which is just this expression with the intermediates of mu and lambda taken out, is now more nonlinear functional than this was. If this was linear, this is not. If this was nonlinear, then this is more nonlinear. And the content of renormalization is just that F prime for different mu's and for mu prime and mu should be the same. So almost a trivial statement now. That's a more complicated argument, but still it argues possibly more compellingly for some. We should allow and expect F measurements to be nonlinear in the test functions. So how do we push this forward? Going to sort of elementary textbook level, we'd construct a generating function for the time-ordered vacuum expectation values, which would look very much like this and is pretty much fairly quickly derived to be in something like this construction. But this, of course, is not well-defined. If we want it to be well-defined, then we should introduce interaction parameters, blocking, and scaling, if we're going to follow a Kadanoff type construction. And so we put those explicitly into here. But one of those is not like the others, because we can quite easily define rescaling only to transform the free field M of X into different free fields with different masses. So instead of being a functional of M, we make it a functional of many different free fields. And together with, we modify the interaction parameters and blocking so that to accommodate the way in which we're describing the way we do the rescaling. But this puts us in a situation where we can use the Riesz-Leiter theorem, because local operators acting on the vacuum vector can approximate any vector. And in particular, we want to approximate this vector that we constructed on the previous slide, which we're going to use to generate smeared 4-point vacuum expectation values, for which one contribution would be the Feynman diagram we see here. But we can also approximate that, which is well defined because it's not the Poincare, it's not the pure Lorentz invariant construction. Construct that with what I'm calling a many-fragment resonance, in which everything is a 2-point resonance, but now between nonlinear constructions. So this is an inverse problem. We're looking for local nonlinear fragment functionals that give us the same results with the right free fields as we get from our best path integrals, as I put it here. Now, I hope we can find something better than this construction, because this is quite sort of not mathematically sophisticated, it seems to me. But nonetheless, we can construct well-defined Poincare invariant models of this that are in line with this. And I'll show you that after this slide, which says, what should our weaker Whiteman axioms look like in that case? I suggest we should say some finite number of measurement operators that are nonlinear in the test functions instead of being operator value distributions. We have a manifestly Poincare invariant state that gives us, by completeness, the GNS construction of a Hilbert space. And then if we need it, we can go to a representation space for the Poincare group by using a direct or inductive limit. Then we have two choices. We can either choose to use a quantum field theory option of spectrum condition and macrocausality, or we can go for the quantum non-demolition field theory of universal measurement compatibility. And as we've seen, there can, in some cases at least, be isomorphisms between these two, but non-local. And then if we want to discuss global properties, then we can do whatever we like as far as I'm concerned. Now, I've argued that linearity is unjustifiable as an a priori assumption. However, if you weaken the axioms in this way, you end up with so many models, you barely know what to do. And I don't know what a good extra axiom that would limit us physically would be. So what I'm going to present to you now are 3 slides of 3 quite different constructions, none of which I want you to take seriously, but just to indicate the kinds of variety that are possible. If we were doing an ordinary construction in quantum field theory of a 5-fold deformed scalar theory to satisfy the Klein-Gordon differential operator together with deformation, then we would use a time-ordered unitary evolution in which we put in the right Lagrangian structure here. And that's equivalent to constructing the deformed theory as a sum of a free field theory with a retarded Klein-Gordon propagator with the deformation we had before. And that's just to insert into the backward light cone measurement operators in such a way that m hat of x still satisfies microcausality. And that's ensured by the way in which we construct this. We usually say that the crowd surrounds m of x, the x point, but we can also say it trails behind. This is not a familiar construction to people, but it's actually quite simple to derive. So if we follow this, we instead might want to do something like construct a recursive cloud of measurement operators within the support of F. So we'd take, at each level, we'd construct the deformed measurement operator at that level in terms of a free field together with a deformation that looks a little similar to what we have here. And I won't dwell on that because of time, but still, this is clearly something that is still local, still satisfies microcausality. So a second construction. We have for the smeared 2-point test function for a Gaussian field, the smeared 2-point vacuum expectation value, we'd have the linear contribution we'd know and love, but we can add to that now a nonlinear construction where we can take these functionals to be anything that satisfies the support condition that the support of the functional applied to F should be a subset of the support of F. So that could be the square. It could be F times almost anything, actually, but in particular, it can be times a Lorentz invariant propagator in convolution with the test function F, or it could be almost an arbitrary function that just has maps 0 to 0, so that at infinity it is still measurable. This has to be finite after all.
How well understood are the non-Gaussian cases?
The non-Gaussian cases I'm going to come to next, I would say I understand some ways of constructing them, but I understand some ways of constructing them. And I'll present one of them, and I'll argue that I want mathematicians to do something better.
Okay.
Here we have, this can be written by using the standard rules of how we write a Feynman diagram. We can present that just as this Feynman diagram. So in these terms, this is essentially, this is an interacting field theory in that way. We construct a 4-point vacuum expectation value that looks like this. Now we can also do, and I'm going to skip these two because of time. So the non-Gaussian case, simplistically, we can just construct an F measurement just as a function of many constructive fields with different nonlinear functionals in them. And that gives us a subalgebra of the Gaussian algebra that's generated by the constructive fields. So what I would like to see would be other ways of constructing subalgebras of those free field algebras using the nonlinearity we now have as a resource. And this comes back to something that's due to Wayne Polozou. Because F measurements are nonlinear functionals of F, we can now take functional derivatives of that and construct multi-point operator value distributions. And this recalls Wayne's and his collaborators' work on the Poincare invariant quantum mechanics, where they use this kind of construction for bound states. But in this case, F measurements may not be expressible as a functional Taylor series, which in particular is not going to be the case here for either of these two. These have finite convergence regions. And in that case, test functions may wrap around singular points, potentially resulting in discrete structure. So this is a way of introducing discrete structure within this way of constructing a non-Gaussian, or indeed actually a Gaussian field. So thirdly, I point out that if we work with an interacting electromagnetic field, then we'd expect the Wigner characteristic function will be different from that for the free field. We might say that the F measurements, the deformed F measurements, introduce fermionic and other clouds, but if we only measure the electromagnetic field, this still should be a manifestly Poincare invariant expression in terms of just the lambdas and Fs. It may not be easy to express it, but on the other hand, it gives us a way to approximate how the physics is without necessarily concerning ourselves about fermionic operators. And indeed, if we know everything about the electromagnetic field at all length scales, and by that I really mean 10 to the minus 100 meters and all scales, because none of this is singular. You can feed in any size, so long as it's not zero, any size test function. And that tells us all about the currents because of Gauss's theorem. So what more do we need to know than that about the clouds? If we know the electromagnetic field everywhere, that tells us an awful lot. And yes, I'm hand-waving because I don't understand fermionic fields well enough. We will just pass over that. So this is a concise list of the difficulties of quantum field theory that I took from recent article from Olderfredi and Oettinger. These 5 problems. Divergences, which I suggest we can address by the nonlinearity I've introduced, and it's a non-dynamical nonlinear resonances, effectively. It also allows us to say, well, there is a precise ontological picture, because we have a signal analysis approach in which we can analyze, we can measure at arbitrarily small scales. There is no between. There's nothing that isn't included in the model. The model may be wrong, and indeed will be wrong, but nonetheless, everything is included in the model. We really can produce quite a good model for almost anything. And I also argue in the last but one slide that, this. So also, as they point out, there are no particles in quantum field theory as such. But by introducing the nonlinearity, weakening the axioms, that means there are more models. And in particular, nonlinearity together with dispersion allows us to construct, I suggest, certainly caustics, almost certainly solitons, which hopefully would be tables and chairs in the long run, very much the long run. Then we have Haag's theorem as a problem, but nonlinearity allows us to construct subalgebras of an algebra generated by many free fields, as I showed you in this earlier slide, which definitely gets us around Haag's theorem in the first instance, at least. And then finally, we have the measurement problem, which I will discuss shortly. So this is the one slide about quantum gravity. I've suggested that for a Gaussian state, all we need to be able to construct a quantum field theory, a quantum theory, is a positive semi-definite matrix in which this matrix is positive semi-definite, and it doesn't matter what the descriptions are, so long as we have a good formula for taking any two descriptions and giving us a result, and the matrix of values is a positive matrix. So the matrix doesn't have to be linear in those two descriptions. And the domain and the manifest symmetries of the matrix fix the theory completely for a Gaussian state. If we want to construct interacting fields, we introduce and combine many such matrices while ensuring that the properties required for the Wigner characteristic function to be a state are satisfied. We just have to make sure this satisfies those constraints. And as you've seen on the previous slides, it's actually too easy to construct such a thing. We can do almost anything. Now, for gravity, we have to describe how we measure the geometry of spacetime. So we need a descriptions to go into this matrix. And if H bar appears non-trivially in the construction of the matrices, then it's quantum, I would say. And if it is locally Lorentz invariant instead of globally Lorentz invariant, then it's gravity. Very broad strokes. And I don't know what a diffeomorphism invariant structure of this kind looks like. My differential geometry is not up to that. But then finally for this, the relationship we have between quantum field theory and quantum non-demolition field theory of the bullet operator, the bullet involution, might give us a path to something that indeed many people have said, well, gravity should be classical. This says we can have it so long as we're willing to work in terms of quantum non-demolition gravity. So now to go on to how I think we can particularly think about measurement incompatibility in terms of signal analysis and data analysis again, rather dropping down from the theoretical level that I've been following before. This is Gregor Wies's experiment from the 1990s, and this is page 60 from his thesis, with the translations are his from a few years ago. And what I particularly like about this is that he talks about pumping the apparatus. He doesn't talk about injecting photons into the apparatus. He talks about pumping, and I'll say he's pumping the electromagnetic field. He's pumping the noise. And so he pumps the noise into there, and then Alice and Bob both have an avalanche photodiode. They have an electro-optic modulator. They have a random bit generator that sets an input to that modulator, and then a clock. And then he's absolutely explicit about the hardware taking the signal from those two avalanche diodes and deciding when to record, the time at which an event happened, and which of the two bits, which of the two diodes triggered, and what the input to the modulator was at the time. So he records just when an event happened and what the two bits are. And that's a very compressed record. It doesn't say anything about what the signal details out of the avalanche photodiode are. We could be recording every few picoseconds, but we don't. We just record the event time. And of course, that's enough for his purposes in the 1990s. So this is the actual data from one particular run of his experiment, in which Alice saw 400,000 events. And on this graph, there are 15,203 events actually displayed, when Bob also records an event with 3 nanoseconds. So there's a very large oversupply of events close to synchronous coincidence. And when they do record an event within 3 nanoseconds, the majority, with the color scheme I've chosen here, are green or yellow. And the color scheme is, for the reds is the diagonal, where the APD and electro-optic modulators for Alice and Bob are the same. The yellows and greens are off diagonal, and the blue is the lower off diagonal. If we turn that around and take 100 vertical slices of that, and add up how many of the events there are for each of the 16 events for each of those slices, we obtain these 16 histograms. We add up these numbers to the numbers in the histogram, we get these 16 numbers. We feed these into the standard, by now, algorithm for the CHSH inequality. That gives us 2.714. That is a violation of the Bell inequalities. What we've done here is we've taken a completely classical data set. We have applied a completely classical algorithm, and we obtained a number for which classical physics says this is not okay. Somehow, classical mechanics is not happy with this. Now, I'm going to argue that in quantum mechanics, what we do to model the violation of Bell inequalities is we use non-commutative operators. And this is something that's in the literature since the early 1980s. In classical mechanics, as usual, we don't have non-commuting operators. What people say is classical mechanics is commutative. Without it, classical mechanics, I suggest we should say, is computationally incomplete. So I'm going to answer in the next few slides how we can add non-commutativity to classical mechanics so it's as powerful as quantum mechanics. Now, I don't want to diminish the role of non-locality because there's a lot of literature about non-locality and Bell inequalities. But specifically for Alice and Bob, if they'd chosen a rate at which they modulated the electro-optic modulation device much slower, then it wouldn't probe non-locality. Equally, if Alice and Bob were very close together instead of being very far apart, it also wouldn't probe non-locality. I don't want to say non-locality is unimportant because for quantum fields, it clearly is. Locality is closely associated with non-commutativity because of microcausality. But for me, non-locality, I don't care. Everyone's so concerned. Well, everyone. A lot of people are so. But quantum mechanics, quantum field theory, quantum non-demolition field theory are like thermodynamics more than they're like classical mechanics. It's like thermodynamics, like a local thermodynamics in particular, where you measure the temperature locally, not at a point, but just in a small region, just as we would say with a test function. So that results in something like the heat equation, which of course depends on boundary conditions in a way that classical mechanics does not. That's as much as I'm going to say about non-locality. How do we present classical mechanics? Typically, we say there's an algebra of functions on phase space, has three binary operations, addition, multiplication, and the Poisson bracket. This is not your standard high school algebra, is the way I say this. But we can make it much more like quantum mechanics by introducing two classes of operators, multiply by W and Poisson by W, for which the second we have the familiar example, Poisson by the Hamiltonian function, which is just the Levinian operator, differential operator. So, of course, multiplications don't commute, but the Poisson operators don't commute. Sorry, multiplication does commute. Poisson operator does not commute with multiplication, nor does it commute with itself. Now we have a non-commutative algebra with two operations that is much, much closer, indeed, very close indeed, to quantum mechanics sort of algebraic structure. And I suggest that we don't restrict ourselves. We don't tie our hands behind our backs. Then we can use both the Y's and the Z's of something that's much more powerful than classical mechanics, what I've called CM+, and it gives us an algebraic measurement theory that's exactly the same as that of quantum mechanics. So with this construction, we don't have to use quantization and the correspondence principle. It's not that we shouldn't, it's just now we have an alternative. So that was very general. For the simple harmonic oscillator, the Poisson bracket is straightforward, just as usual. And we can construct the Poisson by P just as derivative with respect to Q. Same for Poisson by Q as a derivative with respect to P. And so we have these two, which are very reminiscent of the Weil-Heisenberg algebra, except that there's no complex structure. Then we have the Hamiltonian function is just this operator, and we have the Liouvillean operator is this function, this operator. So the natural place to look for a statistical state for this from the 19th century is the Gibbs thermal state at a temperature KT. And I'm going to introduce J again because I want to construct a generating function. And that gives us, for the Gibbs state, a Gaussian expression as you'd expect for a simple harmonic oscillator. Now, because I've introduced J, this now really is the Weil-Heisenberg algebra. And so there's essentially only one mathematical way to go. And the easiest way to construct it is to introduce lowering and raising operators with KT instead of H bar. And of course, the lowering operator annihilates the thermal state. So we can construct modulated, non-equilibrium states, just as we can in quantum field theory, but now with the thermal state. And hence we can construct a Hilbert space. So instead of trying to map classical Q and P to quantum Q and P, we can instead map Q and J partial Q to a quantum Q and P because it has exactly the same algebraic structure. KT is not H bar, however, but there's something really curious about this, and that is that this is just as much about an irreducible noise as quantum mechanics is, because we have here the Gibbs state does not care what the heat bath is. It doesn't care what the interaction with the heat bath is, provided those two together give us a probability distribution for the system we're interested in. This is a good model for it. We are happy. We don't care about what is causing it to be that way. So what is the difference between quantum and thermal noise? There's a simple difference, which is h bar has units action, kt has units energy, different dimensions. In quantum field theory, however, if we look for details, this is where we find it, because we find that the quantum vacuum is Poincare invariant, thermal noise is not. And this is a difference that can be used in CM+. So we adopt that, and we find that h bar is an amplitude of a Poincare invariant noise, kt is an amplitude of a thermal noise that isn't Poincare invariant. This changes everything, because it gives us a new reason to think we must work with field theories. We can only define the Lorentz group in 1 plus n dimensions. The other thing it changes is that h bar approaches 0 is no longer a classical approximation as far as CM plus is concerned. It's a mean field approximation we may well want to follow because it will simplify things a lot in many cases, but it's not a classical approximation. It's just an approximation, mean field approximation. So finally, about classical mechanics, we have for the Gibbs state, the JZH is the Hermitian generator evolution, and it's not a positive operator. The Hamiltonian operator, in contrast, in quantum mechanics, is bounded below. And that has analytic properties that we definitely do not want to give up. It's an incredibly useful thing. On the other hand, I don't want to adopt it into CM+, just because I want CM+ and quantum mechanics to be different so that we can compare them. Classic CM+ does include non-commutativity and quantum noise, which ensures that measurement theory is exactly the same as that of quantum mechanics as far as the algebra is concerned, but it's not analytic in the same way, and that I find helpful. And particularly, CM+ now has a measurement problem. And although the path is not short, it brought me to the argument I'm now going to present you. And that is that if we have two measurements, A and B, with two different sample spaces and presentable in terms of projection operators, then we can construct the probabilities for single measurements of those very simply. This is the Born rule, of course. For two measurements of A first, followed by B, we say that the result alpha M collapses the state to this expression, which you'll find in textbooks everywhere. Then we measure B in that state. So we obtain the result alpha M followed by beta N with this conditional probability, this expression, just feeding this into this. So the joint probability is just this much simpler expression in which this is a positive operator that we can use to generate joint probabilities for the result alpha M beta N. So instead of collapse affecting the state, we can, if we like, purely by convention, it's our own choice, take collapse to affect the next measurement. We can use these positive operator GMN to construct a collapse product, a positive operator valued measure, A collapse B, with a sample space alpha M beta N, even if A and B don't commute. Makes no difference whether they commute or not, you can construct this. Excuse me. But now we have a joint probability. That's something that kind of is classical. So we can instead use commuting operators, A prime and B prime, and a different vector state, psi prime, in a different Hilbert space that give the same joint probability. There's plenty of enough flexibility in all that to be able to construct something that gives us the same result as we get from quantum mechanics construction. This is, in fact, just to use the Neumark dilation theorem to construct a joint PVM for the joint measurement AB that is the same as A collapse B. And that will be in a larger Hilbert space. That's the basis of the theorem. So this is an alternative to using decoherence. It's not a replacement for decoherence, although I like this better, but it is different. And in particular, decoherence takes a large Hilbert space.
Could you explain a little bit more decoherence versus dynamic dilation?
So that's what I'm going to do on this slide,
Okay,
I hope.
Good.
So decoherence takes a large Hilbert space model for whatever's measured, together with everything around it, and shows that the environmental noise will very nearly collapse the state to a mixed state. And for all practical purposes, decoherence works pretty well. Neumark is kind of the opposite. Neumark takes a small Hilbert space for whatever's measured, constructs a positive operator valued measure for a joint that makes us a joint probability, then uses the Neumark dilation theorem to construct us a positive projection valued measurement in a larger Hilbert space. But that's very much more focused. This is describes the effects of a measurement device in the context of subsequent measurements, whereas decoherence really keeps everything very, very wide. So decoherence imagines modeling everything about a coin that we're throwing, for example, and much of the world that surrounds it, and then mathematically reduces that imagined and never actually constructed model to just the two sides of the coin. Whereas Neumark is just a sort of more engineering sort of approach in which we take two sides of a coin and we work with their probabilities, and we're quite happy with just measuring relative frequencies. And then later we come along, we take videos of someone throwing the coin and we examine the dynamics and everything. This is not to say decoherence is better than Neumark, although we might have preferences one way or another, depending on our sensibilities, but we can use either. So we can think of what we've just constructed as, I suggest, a super Heisenberg picture. Both unitary evolution and collapse are applied to measurements. And that's in contrast to the Schrödinger picture and the Heisenberg picture, which does both unitary and collapse to the state, or one to one and the other and not to the other. But this I find very unifying, because if we focus on the classicality of this, just that everything commutes, and that for Bohr, measurements affect other measurements. This is something that you find all through his writings. Then we could call this the Bohr picture. But if we focus on the commutativity in particular, we can call this the quantum non-demolition picture, or indeed we can call it the consistent histories picture. If we focus on the no collapse aspect of this, which I'm going to talk about in the next slide, then we have something we could call the Everett picture, except branching in this construction is not construction is not something that's necessary. We want to have it optionally. Or even we could call it the Einstein picture because it's rather classical, provided he's willing to accept the idea of a Poincare invariant noise. Who knows? So there are ambiguities when we're describing many collapses, because this collapsed product, everything I've tried to construct is actually not an associative construction. So instead of the Heisenberg cut, we actually have a Heisenberg bracketing it's not very clear which choice we should make in many cases. Where this comes into its own, I think, is when we consider signal analysis, where we're actually performing millions of measurements, all at time-like separation, so they all don't commute with each other. After every measurement, you'd have to have a collapse if you were doing the conventional sort of quantum theoretic, everything collapses. Whereas we can, in a quantum non-demolition perspective, just use all commutative operators at different state to obtain exactly the same joint probability. That's the aim of the game in this, is to produce the same joint probabilities. So very quickly, I'm suggesting that collapse is not only or necessarily a dynamical process. You can think of it as that if you like, but it's a conventional choice. We can also think of it purely in terms of just probability theory, no dynamics whatsoever involved. And this is something that you can find, at least in prototype, in the literature. And I'm going to skip this because it just says that quantum mechanics is better for some things, classical mechanics is better for other things. Yeah. So, almost finished. You can find no end of comics that say correlation is not equal to causality. But what do we have to add to correlation to give us causality? One answer you can find in the philosophical literature on causal modeling is that we should add interventions. So we talk about, they introduce this notation in which they say, well, we set the knob to the value x, and then we try it again with the value x1, and we see how the probabilities change. x2, see how the probabilities change. And that gives us an idea as to whether changing the setting changes the resultant probabilities, so it gives us an idea about causality. And that indeed is when you say, well, I'm switching the knob from one setting, it's transformation of the apparatus. And causal modeling introduces graphical and logical tools on top of classical modeling so that they can do this. but the Poisson bracket gives us a transformation algebra. That's what it does. And that can model interventions in an intrinsic and classically natural way, just as we do in quantum mechanics. We have the same tools of non-commutativity available to us in CM+. Now, classical mechanics can model these things by adding graphical and logical tools on top of itself, but classical mechanics can do it in a nicely systematic way that is at least sometimes going to be appropriate, just as quantum mechanics is very often appropriate. So, I've argued that signal analysis and a reanalysis of renormalization suggests a particular introduction of nonlinearity into the Whiteman axioms. I think we have to think about systems just as systems. They're not quantum systems and classical systems. Both at any scale admits a quantum description or a classical description. We use whichever one is appropriate and most useful. Instead of collapse of the state, we can use the quantum non-demolition picture if that's convenient, but we can also use non-commutativity whenever that's useful. Now, I find, when I look at the literature on this material, that quantum and classical physics have been converging in many ways for decades. And I'm trying to channel that in terms of the signal analysis, but I'm sure it can be done in other ways. Now, one thing I will add here is that yesterday morning, I got a rejection slip for the paper that is largely the basis of the first part of this talk. So I am, oh dear. But otherwise, I'm actually quite content with the material. And indeed, the criticisms seem to be, I've yet to really feel comfortable with them, but the criticisms seem to be they didn't like my writing style. I haven't proved enough. The use of the Riesz-Leiter theorem is obvious. And so I guess renormalization is going to be done this way very soon because it's so obvious. So thank you for your attention. Well,
thank you very much. Thank you. So if the quick question,
Yes, I'm sorry.
I guess the classical versus quantum is also part of Osterwalder construction because you go from relativistic fields to Markov fields.
Right. Well, there, of course, the QND construction.
Euclidean fields. So,
right, except that everything I've done has been not in an OS sort of formalism. Everything has been Minkowski.
I totally agree. Yeah. So I guess you go back to the foundations.
Well, and then you also have that, as you saw, the negative and positive frequency is quite similar to what you see with the with reflection positivity in a way.
I think so. Yeah. Right.
But on the other hand, I've tied this much more to the Hilbert transform in signal analysis, or in not just signal analysis, of course.
Yes.
So that seemed to me to be, but in any case.
Yeah, that's good. Okay, fantastic. So we're very happy that you agreed to speak and that right, and think you explained everything really well. And if let's call for a small question.
Right, if anyone would like to, but. Yes, I'm sorry I've gone a little more over.
Thank you very much, Peter. And so we'll right. I think we better click the goodbye.
Thank you.
Right. Thank you very much. Yeah, thank you. Yeah, bye bye.
Bye bye. Bye, Catalina.